Hello, welcome, and an excellent evening. It is again Christmas time, roughly, so we are back with a special Christmas episode for Let's Code MS-DOS, where we usually take DOSBox or real DOS PC and program using TurboC 2.0, but during Christmas we switch to PowerBasic. So if you want to play along at home, you have to have PowerBasic version 3.2 or higher. I think there's also 3.5, but I like 3.2 the best at the moment. It should be available online somewhere on certain sites. There's definitely a demo version that works as well. It just doesn't produce exe files, but compiles into memory. So for testing this stuff out, it's definitely good enough. And if you have an older version like version 2, there might be certain subtleties with the basic syntax. For example, when I'm using variables here and there, the typing of those variables will be different, so you might have to change the code. And during Christmas we also take Christmas topics, and we already had snowflakes produced by so-called L systems. Those are iterative fractal systems or function systems that can produce stuff like trees, plants, but all kinds of weird geometric shapes. And we use the Koch curve to produce interesting snowflakes, basically. But today I want to produce these nice Christmas trees here, and I think this doesn't look like a Christmas tree in this direction, but if we are turning the thing upside down and maybe produce a little bit more iterations, it looks quite Christmas tree-like to me, I would say. And we can reuse most of the code, but I will type it from scratch anyway. With L systems you always have a starting axiom with which to start. Here it is just the symbol f. If we take two f's, we will get two trees, or three, or four, etc. You get the idea. And there's a term replacement happening. Every f is replaced by another f. The square brackets mean a push and a pop of the current state of the machine, and the state is always the current position in x and y coordinates plus the angle of rotation. And in the end, f means to draw a line a certain length, which is also a parameter normally. It is not used here, it's implied. But we have it as a special parameter. So this means actually forward, draw forward. And if you choose to stop after 5 iterations. After the first iterations you first apply all these rules with a push and a pop, and plus and minus mean turn left or right by this amount of degrees, so 36 degrees. And if you apply this, you will get this nice fractal shaped tree, or tree shaped fractal, the other way around. Well, enough talking. We will use a lot of global variables, which is not good in a general sense, but it makes reading this particular code much easier instead of having us to pass around a ton of parameters. In real life I wouldn't do that, but for this demonstration it is actually pretty apt. So as I said, we need a parameter length. Shared means it's a global variable and it's a double. I could have also just written it like so, or I think like this is a double variable, but I like to write out the data type exactly. Col as the color, which is obviously an integer from 0 to 15, because we're using 16 color VGA, high res mode. We have a scale, because this will be like a screensaver, and we will draw a bunch of trees with different scales. This is again a double. Then we need the current state of the L system, as I said, something that can be pushed onto a stack if needed. That is the angle, which of course is again a double. Then we have the position in the x, also a double, and the position in the Y also as a double. That's pretty neat. Stacks for push and pop. There's no stack structure. The only useful structure that we can use here is an array. So we will have 3 different arrays. A position stack for x from 0 to, let's say, 16. Doesn't really matter if we're using only 5 iterations. The maximum stack depth that we'll get is 5. But you could technically use more brackets or brackets inside of brackets, and then it could get bigger. I'm keeping it small here. For this example, it's enough. If you see an array out of bounds, then you might want to increase this. And remember, it could increase exponentially depending on what kind of formula you put in there, because let's face it, you could also produce anything that's in here, but you would have to enhance our code to support multiple rules, for example, and yeah, different axioms, for example. So we're not gonna go into that. That's maybe for some other video. That would take way too long to explain and implement. And we need a stack for the angle, actually, which we'll call the angle stack. So that's that. Those are all our variables except for the stack pointer, because we need to have a stack pointer, which we call SP, just like the stack pointer on the 8086 CPU, and that's just a simple integer. Then we can implement the different functions that we need, or subroutines. The first function is the push, which is called when we encounter the opening square bracket, and we will just code it as push here. And as an exercise, you can, for example, also try to parse a string and produce the function from that, but we will just hard code it. It's easier. So push works like this. You take the stack that you're currently having and put the value that you want to push into the position of the stack pointer, and then you say stack pointer is stack pointer plus 1. Now we pushed something onto the stack. And of course the same goes for the other 2 stacks, the position Y and the angle stack. And that's already our push function. And the pop obviously is very similar, but the other way around. First of all, before doing anything, we need to decrement the stack pointer so that we can get the correct thing here. And of course the roles are reversed. We are taking something out of the stack, which makes much more sense if we write it like this. And that is already basically basically everything we need for push and pop. And this is something that we didn't have in the old code, basically. That was not there. It still compiles, that is a good news. Then we have the function that actually draws something. Draw one step forward. That one didn't change much, except with the push and pop I needed to actually take care of the coordinates explicitly, which we didn't do before. This needs the length as a double and the color as an integer. And what we're doing here, I like to declare all the variables even if it's not needed. We will have a new position, which is a double, and a new y position, also double. And the new position is the old position that is currently there, plus the rotation around the angle. For the x, that's the cosine, times the length, which is the scale times the global length that we defined. But you will see that in a second. Same goes for the y position, but this time, of course, with the sine to get the rotation. And that's that. And then we can draw the actual line from the old position. And in BASIC you take these tuples and write a dash, so it's line from point 1 to point B. Very intuitive, I would say, using the color that we got. And then we have position x is the new position x. And the same, of course, for the y position. Does this still compile? Oh, I accidentally quit. Yeah, still compiles. Perfect. That's very nice. This is still a complete program. The turn is as it was before, turn degrees as double. And the angle gets updated by adding the new degrees times 3.14159.265 divided by 180. This is basically converting from degrees to radians. I'm not going to explain that. That should be obvious, hopefully. And then comes the actual function. That is the function f, which is this substitution here. So we want to write whatever is right of the equal sign into this thing, right? So this takes only n as an integer, which is something that I improved upon from the last implementation where we had to pass quite a bunch of parameters, but now we only need our recursion parameter n. And our formula is supposed to be f push plus ff, pop, push minus ff, pop, then f, pop, push minus f, pop, push, pop, push, pop, push, I think, yes, plus f and f. Okay, how do we code that? Very simple. Every f is just fn minus 1, so one recursion step. Then opening brace or opening bracket is push, plus is turn by plus 36 degrees. Then we get f minus 1, fn minus 1, and a pop, and again a push. Then we get a turn minus 36 degrees, fn minus 1, fn minus 1, then a pop, fn minus 1. Next up is a push, turn minus 36 degrees, fn minus 1, pop, push. Now I have to look up pop, push, then turn plus 36 degrees, first fn minus 1, then the pop, and then one more fn minus 1. Is that correct? Yes, there's an f at the end. Okay, this should still compile. Yes, it does, because there's nothing that we depend on that's not defined here. So, as I said, an exercise could be to have this as a string and create automatically this code, or interpret it as code, basically. We're pretty far already. This does it. Then we need the axiom, the start, basically. I call this XMas. And it gets the maximum iterations as an integer. The higher the number, the more detailed, but also the slower everything will get. And since we're drawing many trees, we have to reset the angle and stack pointer. So angle is reset to 0 and stack pointer is reset to 0. And to have the tree point the right way up, we do an initial turn. We could have also initialized the angle, but I was too lazy. And this is more readable, I would say, if you say turn 90. And then we call f, just in the usual manner. This is basically the starting axiom. Here you could also write fn-1 and fn-1 to draw two trees, obviously. And you can play around with this naturally. Okay, then we switch to graphics mode, and so we don't forget it, we also switch back to text mode. This is 640 by 480, 16 colors, so you can actually see something and have a couple of colors on screen. Then we initialize the angle the first time. Actually, that's actually not needed because we have that here in the XMas routine. So let's leave that out. It might be in the final code that I post online, but yeah. Then we need a count variable, so we can clear the screen every once in a while. And we do an infinite loop, which is only infinite as long as you don't press a key, which works like this, while instat equals 0. You can look that up in the online help, which is very nice. And this is a German version, so we have a German text, but it says, it gives you the input status of the keyboard. And it's 0 if there was no key pressed. So this continues until you press any key. And if the count is greater than 10, then we do a clear screen and set the count to 0. So every 10th tree we do a clear screen. And if, I would say, which is not quite correct. There must also be a else where we increment the count, obviously. Does this still compile? It does. Very nice. Then we need to compute a scale factor, which will be we should randomize the timer. Randomize timer, which means that we will get different trees every time we start this. It uses the timer of the machine to initialize the pseudo random number generator because we need it here. So minimum scale is 0.5, so it doesn't get too small. You can play around with this, obviously. And yeah, we take R&D times 2. I think R&D gives us something between 0 and 1, so scale will be 0.5 to 2.5, which is, from experiments, it looks pretty nice. Where is R&D? Here. It is between 0 and 1, yes. All right, that's good. Then we have to also create a random position. We will take -160 divided by scale plus R&D times 640, which is obviously randomizing the position over the whole screen more or less, and -120 divided by scale plus R&D times 480. This leads to the fact that the tree might also stick out a bit to the border, overhanging over the screen basically, so it gets cut off. So you get like nice, evenly distributed things. But you can play around with this as well. Color is R&D times 14 plus 1, not F1, 1. This gives us a color between 1 and 15, because 0 is black and that would not be visible. Length equals 2. This gives us a pretty nice length. And then we call XMas with 5 maximum iterations. And that's already it. Let's see if it still compiles. Looking good. and nothing happens. And actually I managed to probably have produced an infinite loop somewhere. Okay, actually it was pretty simple, because of course this is generating an infinite loop because we don't have a end of recursion. So if n equals 0, we actually have to draw something. We have to call the forward subroutine. And I should keep in style here by doing this. So we call forward with the arguments length times scale and the color, which is also a global variable, so I wouldn't have needed that. So there's an else there, and then there's an end if. And this way we don't get an infinite loop, and I'm wondering why we didn't get any Stack Overflow here. We should have gotten. Seems it was very, very impressive here. And there you go, it works. So we get nice, very, very colorful and quite detailed Christmas trees, I would say. And I'm always amazed at these L systems, what kind of things they can generate. They also work in 3 dimensions. You need to change the angles, I guess, to 2D angles and stuff like that. But yeah, it's amazing what they can do. And I think this is a nice little screensaver, I would say. We're currently running on the speed of like a mid-range 486, I think. And yeah, for basic, this is actually pretty decent speed, because the recursive nature and all the line drawing, these are like thousands of lines it's always drawing. It's pretty nice, pretty decent, I would say. But yeah, that's more or less it for today. Thank you for watching. I hope you have a great holiday time, and I think if I manage, I will also put out another regular Let's Code this year. It's already prepared, the code is there, but it's quite a long video, I think, because it's quite a bit to explain. So if we're lucky, we will see this as well this year, and if not, then definitely in the new year. But thank you very much for subscribing, for liking, for commenting. Yeah, please post your own improvements on this program, code some other L systems, I don't know. And I think this even looks a bit like a skull or something. It's Halloween mixed with Christmas. I think I heard about that somewhere. Anyway, that's it, and see you soon. Bye!